T, as you look at here, it's defined as unit weight of soil solid divided by the unit weight of water. So this will connect the solid to liquid, because gamma solid is a solid and gamma water is liquid. So this is a very good parameters to connect the liquid to solid, and this value will be given in the exams if they ask you. Okay. Porosity is always less than 1. So that's, is there any question? Okay then. Indrin has asked, porosity is always less than 1, that is value of n. So you are comparing volume of voids to total volumes, right? So it should be always less than 1, because volume of voids, if you look at here, if you look at here, this is your volume of voids and this is your total volumes, and porosity is volume of voids to total volume, so it should be always less than 1. Very good. For the calculation purpose, in exams they may ask you to calculate total weight of a given soil sample, or weight of soil solid in a given soil sample, or weight of water in a given soil sample. And based upon the parameters provided in the questions, you can choose one of these equations. For example, if they have given you the total volumes and the corresponding dry unit weight, then you can use the weight of soil solid is equal to volume multiplied by the dry unit weight. Okay, this is a very important equation, because some of you must be opting for the constructions. In the constructions, there could be questions saying that if the volume of soil in the construction side is this, and the volume of same soil in the borrow side is this, and these are respective dry density, what is calculated the volume or something like that. In that, what you have to understand is the weight of the soil solid in the construction side as well as the borrow side remain constant. Moisture content can change, water content can change, but the weight of soil solid remains same. So this concept is very, very important. Okay. So other tables given here for you to use in the exam is, if they ask you to calculate any of these volumes, it could be total volumes, volume of soil solid, volume of waters, volume of void, or volume of air. Again, it's depending upon the parameters. You can choose the questions here. Similar is the case with your unit weight. That could be a total unit weight, or moist unit weight, dry unit weight, saturated unit weight, buoyant unit weight of water, or unit weight of soil solid. Okay, let's say if they give you a void ratio and a specific gravity of a given soil sample, and unit weight of water, even if it is not given, you can assume it. In that case, if they ask you to calculate dry unit weight, this is the equation you will use, right? Dry unit weight is equal to specific gravity times unit weight of water divided by 1 plus void ratio. But obviously, you should know the void ratio of the soil sample and the specific gravity of the solids, soil there. Okay. So the other things, the importance identity that you have to know is the difference between the density and unit weight. If you look at here, this is gamma W, which is unit weight, and if you look at here, this is rho W, density of the soil, unit weight of the soil. The difference we can look at by comparing or by defining in terms of the specific gravity. In terms of unit weight, it is the weight of the soil solid divided by volume of the soil solid divided by the unit weight of water. In terms of density, is the mass of the soil solid to the volume of soil solid, and the weight is connected to the mass with this equation, where G is the accelerations due to gravity in English unit and SI unit. In exams, if unit weight of water is not given, you have to take it as 62.4 pound per cubic feet in English unit, or 9.81 kilonewton per meter cube in SI unit. Okay. So let's try to go over this example so that we can make use of the table. You don't have to remember the tables, but if you need it, the question is related to the phase relationship to calculate the volumes, weight, specific gravity, or dry unit or some things, then you need to come to the table number 1 and do the calculation. Let's do this example 1. Please read it once. Yes, Muhammad, the volume of voids is always less than the total volume because the total volumes includes the volume of voids. Volume of voids plus volume of soil solid makes the total volumes. Therefore, volume of voids is always less than total volume. Example 1. A soil has a volume of 0.3 cubic feet, weighs 36 pounds, specific gravity 2.67, moisture content as 18%. You need to calculate moist unit weight or total unit weight. It's the same thing. Followed by the dry unit weight gamma D, followed by void ratio A, porosity, and degree of saturation. So if you look at this problem carefully, the problem states 0.3 cubic feet of volume. So this should be the total volume. It did not say volume of void is so much, volume of soil solid is so much. It simply said volume of the soil. So it should be total volume, and it says it weighs 36 pounds. It did not say the weight of water in the sample was so and so, and weight of soil solid in the water sample was so and so. It didn't say, it says 36 pounds. So without doubt, it should be total weight, and this is total volumes. And from the table number 1, if that's the case, we can pick up these relations. Total weight divided by total volumes will give you the moist unit weight or total unit weight. So 36 divided by 0.3 will give you 120. Calculation wise, besides these parameters now, you also know one more parameters to calculate these remaining parameters. Next is your gamma D. Again, if you go to table number 1, the relations with the gamma D versus total unit weight or moist unit weight is this. Whatever moist unit weight you have or total unit weight you have divided by, if you know the moisture content, then you can calculate the gamma D by using this. In this case, we know the moisture content is 18%. Therefore, gamma is 120 as calculated here, divided by 1 plus, in the calculations, you'll put the whole number. So 18% will become 0.18. So it will be 120 divided by 1.18. If you plug it in the calculators, you will get 101.7 pound per cubic feet or PCF. Okay. Now again, to calculate void ratio from table number 1 is actually before in relations between gamma D and void ratio with specific gravity and unit weight of water. This is the relations. That relations, whatever I showed you, if you work in terms of the void ratio, it takes the form of these equations. Here specific gravity is given, unit weight of water not given in the problem, but we can assume it 62.4 pound per cubic feet because all the units are in pound per cubic feet. Divided by gamma D, we just calculated here. So if you plug, you will get 0.64. Now once you know the void ratio, porosity can be easily calculated from table number 1 because porosity is directly related to the void ratio with these relations. Void ratio is known here. Therefore, if you plug, you will get 0.39. Degree of saturation, again from table number 1, this is the equations you will pick up because moisture content is known, specific gravity is known, void ratio we just calculated here. So in the calculation for the moisture content, again you will put 0.18, the number, specific gravity 2.67, and void ratio 0.64. If you do the math, you will get 0.75, close to 0.75, and present the answer in percentage multiplied by 100, so it will be 75%. This is how you will perform the calculations. In the mornings, all of this will not come, maybe one of these short calculations, one of these, okay? But if you know where to find the equations and how to do the calculations, it should not be a problem. Sometimes they may give you the questions on this phase relationship, okay? Again, if they give the questions on the phase relationship, go to the tip. First of all, understand what is to be calculated. Read carefully and look for that things, whether it will be a volume, whether it could be a weight, whether it could be a unit weight, moisture contents, void ratios, degree of saturation, whatever it is. Go to the table and look at the parameters given to you in your problems and find the correct equations. So that should be your strategy. Gamma W will be, even if it is not given, you can take it, Lois, alright? Oh, should be here. So as I told you here, typical unit weight of the water is as follows. So in exam, even if it is not given, you should use it 62.4. NCEES handbook give us this value, so we are allowed to use this value. So sometimes they may not give this value at all, but in your calculation, if you need it, use this value. That's what we did here, right? Here we needed the unit weight of water, that's why we used 62.4. It was not given here. Okay, very good. Georgie, sorry, I said Louis, right? Louis tell is 62.4. All right. The other things important also is your relative density. When you talk about density, whether the soil is loose or dense, it's give a sense of density, right? So is comparing the density of what soil materials. So the relative density can be defined in terms of void ratio or in terms of dry unit weight. Relative density dr is related to the void ratio with these equations E max, E minimum, and E. E max and E minimum are the void ratio determined in the lab. E max represents the maximum void ratio the soil can take, the soil can exist, and the E minimum is the minimum void the soil can stay or can take. So E minimum means the voids are very, very small, so soil particles are close together. So this will give you a dense state. When you are saying E minimum, the soil is very, very dense. And when you say E maximum, soil particle far away, there is a big voids, therefore it will give you the loose state. So again, this E max, E minimum are determined in the lab. This E is important for us. This E is the void ratio of the soil in the field. Okay, so sometime if you know the relative density, then you may have to calculate the in situ void ratio using this equation, or if you know the in situ void ratio and E max, E minimums, then you can calculate relative density using this equation. Similarly, if you know the gamma D minimum, gamma D max, these are the value determined in the lab for a given soil sample, and gamma D is their in situ void ratio, in situ dry unit weight, then you can calculate relative density using the equation, or if relative density is known, you can convert this equation in terms of gamma D and you can calculate gamma D. So these are the techniques. So basically it will give you the relative density of the soil, and relative density of the soil is important because if the soil is, as the relative density increases, the frictional angle increases, right? So if the frictional angle increases, your bearing capacity factor will increase. We'll talk about it afterward. So this relative density, we will use this concept in chapter 3 again. So let's do an example. So sometimes if they give you example vertical calculations based upon relative density, that could be something like this. So please read it. Problem says a given sand sample, and these relative densities are only for sand and gravel. These are called coarse material, not from silt and clay, because silt and clay is controlled by the plasticity, but sand and gravel is controlled by the grain size. So this relative density is referring to the sand and gravel. Therefore, this example is talking about sand. For a given sand sample, laboratory test give you Emax is equal to this, E minimum is equal to this, specific gravity of the sand is this. Then the relative density using the standard Peterson test was approximately 65% for that sand. You need to calculate gamma D, dry unit weight. If you had gamma D max and gamma D minimum, then you could have straight calculate the gamma D because relative density is given. But what is given here is E max and E minimum and relative density. With this, you can calculate the in-situ void ratio. So let us look at what are the things given here, and we'll try to know what are the equations we have in table number 1. The parameters given in this problem is E max, E minimum, and relative density. Using these 3 parameters, we can solve relative density equations to find the in-situ void ratio. Then what? If you find the in-situ void ratio, how it's going to help you? Then let's go back and look at the table number 1. If you look at the table number 1, we know we have these relations because we have been asked to calculate dry unit weight. So in the table, I will go and look for the gamma D because gamma D is the dry unit weight. When I look at the gamma D tables, then one of the equations gives you specific gravity, which is given, unit weight of water, even if it is not given, you can assume it, and void ratio, we just calculated it, right? Then why not to use this? So if you use these equations, if this is the void ratio, so if you use these equations, that means plug these values and you will get gamma D, and which is the parameters has been asked there, right? You have been asked to calculate dry unit weight of the sand, and you did. So this is basically using the different equations presented in the table, depending upon the parameters given in the problem. Okay, very good. That was a brief review on phase relationship. I know you have been through this phase relationship in your class, but it was good to review with you. Now let's review on index properties and soil classification. Sometimes they may put the questions in regards to the index properties and soil classification. Index properties means index are number, a number without any units. These are just a number, right? So when we say about index property, we are talking about index properties of soil. Once we review the index property of the soil, then we'll go and classify the soil. Okay, there are 3 types of soil classifications that we'll review. One is ASTO, one is Unified Soil Classification Systems, another one is United States Department of Agriculture's textual chart. So all of these will need the index property, right? Or at least particle size distributions, they will need it. So let's go and see. Grain size distributions or particle size distribution of a given soil sample is performed by using the sieve analysis here, as given there. So I know you are aware of these sieves. Anything not passing through number 200 sieve or particle size as 0.075 milliliter greater than this are called coarse grain soils, and that will give you the grain size distribution. Anything passing through this number 200 sieve as well as some fine passing through number 100 sieves, we will run the hydrometer analysis to get the particle size distribution of the fine grain soil. Okay, all these my references is referring to the School of PE's exam review guides, breadth, published in 2019. Okay, so these are those references. This is in order to understand grain size distributions of a given soil sample, you should have a knowledge of the sieve sizes and sieve opening. So this is your United States or US sieve sizes and in considerations here, and this is the corresponding sieve opening, and this sieve opening is nothing but the particle size, and particle size diameter. Okay, particle diameter is in millimeters. So as you know here, as the sieve sizes increases, number 4, number 10 and all this thing, particle size decreases. So you have to be careful, right? Number 40, number 200 is the smallest particles. That's measures in the US sieves analysis. The sieve number 4, sieve number 10, sieve number 40, sieve number 200 are important because these are the sieve which will separate one fraction of the soil to other fractions, and as we move, we'll talk about this. Let's say your grain size distribution curve for a soil sample is as given here. So when a grain size distribution curve is given, what you have to understand is this is a relation between the particle sizes, or grain diameter is particle sizes in millimeters, to the percentage passing by the finer weights to the different sieves, and the sieves are given here. Okay, so your x-axis or horizontal axis for the grain size is plotted into the log scale. Please be mindful here. Whereas your percentage finer by weight is plotted in the normal scale. So this is 0%, 10%, 20%, 30, and so on up to 100. And these are your sieve sizes. Your sieve sizes 3 inch, 2 inch, 1 inch, and number 200, right? So these are different sizes. So basically a gradation curve is a plot between the grain size with respect to the percentage fineness from the sieves. So the particle size distribution curve will have two indices that we can define from that curve. One is called coefficient of uniformity, which is D60 divided by D10. The other indices that we can calculate is coefficient of conformity, or coefficient of curvatures, or coefficient of concavity, or coefficient of gradations, known as C sub C. C sub Z is D30 square divided by D60 and D10. Coefficient of conformity, sorry, not coefficient of conformity, is I said coefficient of concavity. It's not given here. So sometimes this is known as coefficient of concavity also. So these are the two indices that we can calculate it from the particle size distribution curve, and this C sub U coefficients and the coefficient of uniformity and coefficient of curvatures indicates the general shape of the grain size distribution curve. So depending upon the grain size distribution plot, so depending on the soil type, it will vary. Okay, so let's calculate for this soil because this is given to you. Calculate coefficient of uniformity and coefficient of concavity, or coefficient of gradation C sub C. To calculate coefficient of uniformity as defined, you will need D60, also you will need D10. So what is this D60 and what is this D10? If you know how to read the value of D60 and D10 from a given curve, then you can calculate coefficient of uniformity for that particular soil, because the soil is represented by the curve here now, right? let's say for this soil, you need to calculate C sub U and C sub C. To calculate coefficient of uniformity, first you need to calculate D60. D60 is the, from the 60% percentage finer, draw a horizontal line to the given curve, gradation curve. In this case, this is the curve, right? And rate the corresponding particle sizes down here. So D60 for this gradation curve is 0.5. So what it indicates is, for this soil, based upon this gradation curve, 60% of the particles are smaller, finer than 0.5 millimeters. Alright, 40% are bigger than 0.5, in other words, and 60% are finer than, smaller than 0.5 millimeters. So that's the meaning of this D60. So you know the value of D60. Now you need to calculate the value of D10. But since we have to calculate the value of D30 also, let's find the value of D30, which is at 30%, right? This is your 20%, this is your 40%, so 30% is there. So from 30%, draw a horizontal line and rate the corresponding value of particle size, which is 0.125 millimeters. It has to be all the millimeters, right? Now you also need D10s to calculate your D60 and C sub U and C sub C. So calculate the D10, which is 10%. This is your 0%, that's your 20%, 10% is here. From the 10%, draw a horizontal line and rate the corresponding particle size, which is in this case 0.012 millimeters. You have to be careful, these are in log scale, right? So if you look at here, 100, 10, 1, 0.1, 0.001. So these are the log scales and these are the values. Now once you know D60 and D10, your coefficient of uniformity is 0.5 divided by 0.012 millimeters by millimeters. They cancel out. So this is a number. So this is a indices. Similarly, C sub C, coefficient of curvature, D30 square divided by D60 and D10. D30 is 0.125, and do not forget to make it square, because we have got millimeters here at the bottoms, another millimeter here, so that has to be cancelled out to get the number. Again, this is a index number. Okay, this is how you can calculate C sub U or C sub C. In exam, sometimes they may give you the gradation curve, and looking at the gradation curve, they may ask you to calculate C sub U or C sub C. Right? Any question? If not, let's go over this example and try to go over what we have reviewed so far. Please read the question. So the example 2.1 talks about sieve analysis as shown here. So sieve sizes are given here and percentage finers are given here. Okay, you need to find the mean grain size. Mean grain size means D50. Okay, statically means 50%. So mean grain size is D50. Effective grain size is D10. I think so this mean grain size in your page number 8, if you look at it, mean grain size is D50 and your effective particle size is D10, right? So it means D10s mean 10% of the particles are smaller or finer than D10. D50 means 50% of the particles are finer than D50. So these D10, D50, D30, D60, these are a particle size, as we know, right? So let's do that example. So in this case, what would be your mean grain size based upon this example 2.1? Can you tell me what would be the mean grain size? or 0. So number 30, very good. And number 30, if you look at the ES table 2.1s, then you will get the 0.6. Very good. So this is 50% passing, so obviously this is D50, 60% passings, D60, 30% passing, D10, and 10% passing, D10, sorry, 30% passing, D30, 10% passings, D10, right? And these are the sieve sizes, but these are not the particle size. You have to find the particle size or sieve opening. So from the table 2, you can find the particle size, which are S here. So once you know this thing, then your mean grain size is D10. So for this example, for this problem, your mean grains effective particle size is 0.75, mean grain size is 0.6, and C sub U is 0.85 divided by 0.75, and coefficient of gradation C sub C is 0.6 square divided by 0.85 divided by 0.075, which is given here, right? This is your mean grain size, D50, effective grain size, and coefficient of uniformity, D60 divided by 10, and coefficient of curvatures, D30 squared divided by D60 and D10. Alright. So, let me know if you have any questions. Can I move on? Okay. Now that was the case when your soil particle was granular, like sand and gravel. What happens if your soil particles are fine? In construction site, you have got soils, fine soils as well as coarse soils. The index property that we talked about was for the coarse soil. Now for the fine grained soil, that is the particle passing through number 200 sieves, known as silt and clay, your behavior is controlled by the plasticity of the soil. Therefore, we will define the index properties of this fine grained soil based upon the Arterburg limits. Arterburg limits is, as we know, if you have a fine grained soil, let's say clay, and you completely dry the clay, and at that stage the clay is at solid state. Now if you put some more water, if you add the water and remove that solid state clay, then it will transit to semi-solid state, something like semi-solid, right? And again, if you put some more water, it will transit from semi-solid state to plastic state. At that time, the limit is known as plastic limit. And if you add some more water in plastic state and remold it, it will behave like liquid. It will transit to liquid state. And this limit is called liquid limit. For fine grained soil, liquid limit and plastic limits are very, very important. And these are the value determined in the lab, and it will be given. If they want to test you, this value will be given. What you have to know is plasticity index Pi, which is liquid limit minus plastic limit. Okay? Because there are many tables, charts available based upon the liquid limit and the plasticity index of the fine grained soil. Let's see what's happened when you are transiting from solid state to liquid state. What is happening here? Can you tell me? What is being added here? If you move from solid state to liquid state, so you are adding water, right? So it means if you are adding water, what does it mean? The moisture content of the soil is increasing, right? You are adding water means moisture content of the soil is increasing. So it may so happens in your dry seasons, your construction site is completely dry. Let's say it's a fine grained soil and there is a lot of dust. It's dusting everywhere. Or as it rains, the moisture content of the soils increases, so it might transit from solid state to semi-solid states. If it rains, again it will transit from semi-solid state to plastic state. Your trucks, your dozers and everything will have very difficult times, right? It's because the soil is now acting like a plastic there. It's very difficult to drive through. Even if it is rain more, then it might, whole thing will like a liquid. to drive through the liquid. So you can see these things in construction site itself, right? And that's why you should know this parameter very good. Now, based upon coarse grain soil and fine grain soils index property, now we will use this concept to define the soil. So if you want to read about upper limits, you can read it here. So first of all, we'll take the case of soil classification, which is called ASTO soil classification system, and this system is used for classifying the soil that is to be used as a sub-grade material. It means materials to be used below the pavement. This is the soil classification system adopted by the highway Department of Transportation, so highway, federal highways. So for the roadway constructions, the soil below the roadway will be classified based upon the ASTO classification system, and every system has their one way of defining the particle size. Based upon ASTO, it defines the particles as gravel when the soil is as big as 75 millimeters, or anything passing through number 3-inch sieve and not passing through number 10 sieve, or the particle as 2 millimeters. Or sand, anything passing through number 10 sieve as big as 2 millimeters, and 2 as small as 0.057 millimeter, or anything not passing through number 200 sieve. Silt passing through number 200 sieve, not passing through 0.002 millimeter sieves, and clay passing through 0.002 millimeter sieve and not passing through 0.001 millimeter sieves. Again, you don't have to remember it. If you need it, come to this page 12. Alright? If there is a ASTO classification system and you get confused what size is gravel, what size is sand, then come here and look at here. Okay? Classifications. In order to classify the soils, you have to follow a procedures. Procedures would be such. They will give you the percentage passing of the soil from sieve number 10, sieve number 40, sieve number 200, and if the soils consist of fine soil, fine particle, they will also give you the liquid limit and plasticity index of the soil passing through number 40 sieves. ASTO classification table that I will go very soon is given in table 2.1. During the process of classifications, you have to move from left to right using the process of eliminations until the first group in the table, ASTO table, it conforms the laboratory data that has been given for that soil sample. What does this mean? I will take an example. So when we go over the example, you will understand it clearly. There are shortcut methods to classify the soil. One of the shortcut would be, if the percentage passing through number 200 sieve is less than or equal to 35%, then you need to use the ASTO classification table starting at A-1-A and shortcut. If you have A-1 and A-3, these are the soil type given in that ASTO classification table. We will go very shortly. If A1, A-1 and A-3 are eliminated, then there is another figure 2.3, which is again given by the ASTO. This is a graph from the ASTO. That graph is related to the liquid limit and PI value. You see that liquid limit and PI value. That's why you have to know the index properties of the fine grained soil. Based upon that, you can classify that soil. We'll take an example also. Another shortcut, if the percentage passing through number 200 sieve is greater than 35%, then go to ADS4 and use your process of elimination starting on left and move to our right. Okay. Or shortcut, you could use the figure 2.3 using liquid limit and PI. And if your percentage passing through number 200 sieve is greater than 35%, this is pretty straightforward. You could directly use this figure 2.3. Okay. In case of percentage passing less than percentage passing through number 200 sieve is less than 35%, then you have to use only after A-1 and A-3 are eliminated in the table, then you could use this figure. Below the table, there is a group index called group index. I will show you that. You need to calculate the group index or partial group index using the equations given below, right? And if in the calculation of group index or partial group index, if your value comes negative, report it is 0, and always report your group index or partial group index PGI in the whole number. Okay, whole number. Shortcut. In the table, group A-1, A-3, A-2-4, A-2-5, if you classify your soil as one of these, then your group index GI is 0. You do not need to calculate the group index GI. If you classify the soil as A-1, 2-6 or A-2-7, then you need to calculate this PGI. What does it mean? Let's go over the table now. This is your ASTO classification table. The first thing here under general classifications, look at here. If percentage passing through number 200 sieve, that means 0.075 millimeter sieve, right? That is 0.075 millimeter sieve means 200, number 200 sieve. If percentage passing through number 200 sieve is less than or equal to 35%, so then your soil could be A-1, A-3 or A-2. You need to start here and use the process of eliminations and move toward the right. If percentage passing through number 200 sieve is more than 35%, then your soil could start here. Your soil could be A-4, A-5, A-6 or A-7. Okay. Now, this is the equations from group index GI. GI means group index, which is F stands for percentage passing through number 200 sieve, and it should be presented as a whole number. Okay, and these are your numeric value. LL stands for the liquid limit of that soil, and F again is the percentage passing through number 200 sieves, and PI is plasticity index. So this is the group index equation. If you classify the soil as one of these, A-1-A, A-1-B, A-1-3, A-2-4 or A-2-5, then you do not need to calculate GI value, because GI value for these soils are 0. Okay. If you classify the soil as A-2-6 or A-2-7, then you need to calculate PGI, and PGI is called partial group index. PGI is calculated using these equations. Okay. If in your classification there was a soil sample to be used as a subgrade material for the roadway, you tested it, and when the test result came and you classify the soil as one of these, A-4, A-5, A-6 or A-7, then at that time for that soil you need to calculate the GI, and GI value is calculated using these equations. Okay. If you define, in this case, if you define A-7, A-7 has got two subgroups, A-7-5 and A-7-6. A-7 become A-7-5 if the plasticity index of the soil is less than or equal to liquid limit minus 30. In the example, we'll take a value and go over it. If your plasticity index of the soil is greater than liquid limit minus 30, then your soil become A-7-6. Please be mindful here. This is only valid if you classify the soil as A-7. Right? Under A-7, both is in one column. So under A-7, you need to know whether your A-7 is A-7-5 or A-7-6, and that is dictated by this testing value, liquid limit minus 30. Okay. In this table, you will find NP. NP stands for non-plastic. NP stands for non-plastic, 0 symbol. It means soil is not plastic. Okay. Other thing here is, if you look at here, usual type of constituents materials. From A-1 could be your stone fragments, gravel and sands. Very good subgrade material, right? A-3 could be your fine sand. A-2 could be your silty or clay, gravel, and sand. So the major component is your gravel or sand, but it also contains silt or clay. That's why that belongs to your A-2. And from here to here, the material is rated as excellent to good material for the subgrade, to be used as a subgrade materials, right? To be used as a subgrade material for the roadway, it is rated as excellent to good material. If you classify the soil as one of these, it is rated as fair to poor. You may have to improve the quality of the soil. You need to do some ground improvement or soil improvement or soil modifications to improve the properties of the soils and to be used as a subgrade material for the pavement. Usually your A-4, A-5s are silty soil, and A-6 and A-7s are clayey soils. These are not good material. One other thing here, as you calculate the group index GI, you will get the value, right? Smaller the value, better the soil to be used as a subgrade material. But when you compare the group index GI, that group index GI should be compared for the same soil only. Okay, so let's say you have a two sample from the side, and for example, this is, let's say you classify both the sample as A-4. Then you don't know which one you should recommend as an engineer to be used as subgrade material. Then you know this both of them was classified as A-4, but one of the sample give you the lesser GI value compared to the other one. Then you will recommend the soil with the less GI value. Lower the GI value, better the soil for the subgrade material. Okay, that's also keep it in mind. If you want, you can read it here. Higher the GI, the less suitable the soil. Example, A-6 with GI of 15 is less suitable than GI of 10. So that is valid for if both the soil sample is A-6. Okay? So the GI value is compared for the same class of soil. You cannot compare the GI of A4 to GI of A5. Not in different class. GI of A5 cannot be compared to GI of A6. GI of A6 should be compared to the soil of GI of A6 itself. The soil should be same class. So you can see it here. When your PI is less than or equal to liquid limit minus 30, your soil is classified as A-7-5. When your PI is greater than liquid limit minus 30, the soil is A-7-6. So this happens when you classify the soil as A-7 here. Okay. So I was talking about figure 2.3. This is the astrographical chart. The advantage with this chart is there are different regions here. This is one region, 2, 3, 4, 5. Based upon liquid limit values, plasticity index, and this line here. So there are different type of soil, and each soil type is depend upon the percentage passing through number 200C. Okay, so if you know the liquid limit of the soil, and if you know the plasticity index of the soil, plot the values of PI and liquid limit and look at where does it lie. Wherever it lies, then you will have two values. Either, let's say if it lies here above this line, below this line, then there are two types of soils. That depending upon the percentage passing through number 200C, either you will pick up this or this. Okay, so we'll check an example also. Let's take this example 2.2. Then you should be able to use that table as well as the graph, astrograph. Please read it first. So the very important thing here is determine the ASTO classification. First of all, you should know what is the classification system. In this example, it is stated ASTO. So you have to follow the ASTO classification system to classify the soil sample A, soil sample B, soil sample C. Percentage passings are given here. from these sieves. Also, you are provided liquid limit and plastic limit information here. So let's take soil sample A. When you take soil sample A, liquid limit is non-plastic, plastic limit is non-plastic, therefore plasticity index PI is also non-plastic. First of all, percentage passing through number 200 sieve is 23%. Alright? So you should start from the left, far more left. If you look at here, the far more left, you have got A1 followed by A3 followed by A2, right? If you look at the answers, there is A-1, A-1 V, A3, A-3, A-2, A-4. So all of them are present. So you need to use the table, as2 table, which is this, right? You came to this part because the percentage passing to number 200 sieve is less than 35. This is valid if the percentage passing through number 200 sieve is equal to or less than 35. For soil sample A, 23% is passing, which is less than 35. So the soil could be one of these. You need to start at the left here, far more left. Here, the first requirement is percentage passing to number 10 sieve is 50% maximum. For soil sample A, percentage passing to number 10 sieve is 82%. So that is maximum 50%. So that soil sample A does not meet this criteria. So if this is wrong, then you will move toward the right. When you move toward the right, next requirement is percentage passing to number 46. 46 should be maximum 50%. Percentage passing through number 46 for soil sample A is 46%, so that is correct. If it is correct, you have to move down. When you move down, another requirement is percentage passing through number 200 sieve should be maximum 25%. For soil sample A, 23% is passing, so therefore that is also correct. If that is correct, again move down. Is there any other requirement? Yes, there is one more requirement, which is plasticity index of the soil should be maximum 6. For soil sample A, plasticity index is non-plastic. It's 0, right? Up to 6 were okay, but our soil sample A has a 0. Therefore, that is also correct. So if you move down, there is no more requirement. It is giving you the type of soil, right? So without doubt, soil sample A is your A-1-B. So here we use the process of eliminations to check the percentage passing through different type of sieve of the soils and the upper limits, right? So this is how you will do. NP stand for non-plastic. N for non, P for plastic, non-plastic. It is given below your as2 table. Okay, gyro, you can take a look. If you forget afterwards, look at it is given and below the as2 table. So this definitional sample A could be your stone fragments or gravel and sand. But anyway, soil sample A is an excellent material to be used as a subgrade material, right? So in exams, some of you might be running out of time and want to be clever. You will see NP is here. Soil sample A has an NP, so you might choose this. It has 3. You should not do that, right? You should follow the process of elimination as given here. So for these soils, your group index GI is 0, right? If you classify the soil either this, or this up to here, group index is 0, GI is 0, therefore we will write group index GI is 0. Therefore answers you could write as A-1-B in the parenthesis 0. 0 number in the parenthesis represent the group index GI or partial group index PGI. Okay. Any questions for the soil sample A? Let's do the soil sample B. Okay. If you look at here, percentage passing through number 200 sieve is 30%. So you have to obviously start at the left side, right? Without doubt. But if you look at here, you have got liquid limit and plastic limit. So that will give you the PI. What is the PI of this soil sample B? Can you tell me the PI? Is 11, right? Because liquid limit minus plastic limit in plasticity index PI, 25 minus 14 is 11. So since you have got liquid limit and you have got PI, why don't we use that graph, ASTO graph, the graph given by the ASTO, figure 2.3. That is this, right? So in this case, this is your liquid limit. Start at 0, goes up to 100, and this is your 0, goes up to 70. For the soil sample B, the liquid limit is 25. So that should be in between 20 and 30, this line, 25. And your plasticity index PI is 11, that should be just above 10. So if you plot soil sample B, the point lies here. So that point is above this black line and left of this line. So that indicates it could be either A-2-6 or A-6. So that should be confirmed based upon the percentage passing through number 200 sieve. Percentage passing through number 200 sieve is 30% here, right? 30%, so it should be coarse grained soil. So if you look at it, A-2-6, A-2-6 is here. Therefore, soil sample B should be A-2-6. Okay? So if you have liquid limit and plasticity index, you are better off using this chart. You don't have to run that table. Did you use figure 2.3 because you saw no answer was A-1? Very good. I use this figure because my PI was greater than 6. Alright? My Patrick, I understand you, very good. My PI value of soil sample was greater than 6, is 11. So I use this because liquid limit is given, PI is greater than 6, so I use here. Okay? But as I mentioned before, if you get confusions, you would like to use the table, follow the table. Table is the best, right? So again, use the process of eliminations. Percentage passing to number 10 sieve should be maximum 50, but for soil sample B, it's 74, so that is not correct. If you move here, percentage passing to number 46 should be maximum 50. Here, percentage passing to number 46 is 52. That is also not correct. So we move to the left. Percentage passing to number 46 should be minimum 51. Here is 52. So that is correct. If you move down, percentage passing to number 200 sieve should be maximum 10%. Here is 30%. So that is not correct, right? This 30% is passing to number 200 sieve. So if you move here, you will say all maximum 35, 35, 35, 35. So these are same value, right? So you could in fact check mark all of them because only 30% is passing, which is less than this 35. So if you look at here, liquid limit should be maximum 40, liquid limit is 25, so that's correct. If you come here, plasticity index is maximum 10, your plasticity index is 11, that is not correct. So when you move here, again your liquid limit should be minimum 41, your liquid limit is 25, so that's not correct. If you move here, liquid limit should be maximum 40, here is 25, that's correct. And if your plasticity index should be minimum 11, soil sample B has just 11, so that's also correct. It means there is no more requirement on this, therefore your soil is A-2-6. You will have the same answers. Okay? Table 2.1 is much easier to use for this problem. Yes. Put the value there and just keep on moving, right? Using the process of eliminations, it should be good. But there are two methods, whichever you prefer or you masters yourself, use that method. Now, since this is a A-2-6, you need to calculate partial group index PGI. And the value equation of the partial group index PGI is given by this, right? Second part of that group index equation. This is number, percentage passing to number 200 sieve is 30, put 30 here, minus 15. plasticity index of soil sample B is 11. So 11 minus 10. So when you work out, you will get 0.15. This is less than 0.5, so we'll report it as a 0. It has to be presented into the whole number, right? If it was 0.51 or 0.5, we would report 1. But it is less than 0.5, so we'll report it as a 0, because this is value is 0.15. Therefore, your answer should be A-2-6 and the parenthesis 0. PGI, partial group index, is 0. Okay, any question? Percentage passing to number 200 sieve is less than 35. PI is greater than 6. Therefore, you can use shortcut for granular soils, that is figure 2.3, and calculate PGI. But if you don't want to use the figure 2.3, you could use the table. Yes, Timothy, GI is different than PGI. 100% correct. So this is your GI, okay? This whole equation is GI. We will use it for, and this is your PGI. This is your PGI. Whole equations is GI. If you use only the second half, the second one, it is PGI. Okay? Now let's classify the soil sample C. Percentage passing to number 200 sieve is 87%. So it's greater than 35%, right? So it should start at A4. It could be A4, A5, A6, A7. If you look at the answers, A4, A5, A6, A7, all of them are there. And A7 has two subgroups, A-7-5 or A-7-6. So what is the PI value of this soil sample C? Can you give me PI? PI is 31, right? Very good. Keep it in mind. PI of soil sample C is 31. We calculated it. Now, since you have got liquid limit and PI, let's use the figure 2.3. Okay? If you use the figure 2.3, which is this. Now, your liquid limit is 71. This is your 70, just right up 70. And PI is 31, just above 30. So if you plot, point lies here. This point is below this green line and above this black line. If you look at, there are two types of soil, A-2-7 and A-7-5. And percentage passing to number 200 sieve is 87%, which is greater than 35. So you have to look here. So if you look at here, it is A-7-5 is here. Therefore, your soil sample is that. Okay? But, however, if you want to use the table, no problem. Because percentage passing to number 200 sieve is 87%, which is greater than 35%. It is valid for greater than 35, right? More than 35%. Then you should start here. It has 4. Start here. Percentage passing to number 200 sieve should be minimum 36%. 87% is passing. So that is correct. So if you move down, liquid limit should be maximum 40. Liquid limit is 71. That is not correct. So move the other side. And when you move other side, that's again correct. If you move here, liquid limit should be 41 minimum. Liquid limit 71. So that is correct. If you come down, plasticity index should be maximum 10. Your plasticity index is 31. Not correct. So you move here with the same, you move here, right? Then all of these will be checked. It means without doubt your soil is A-7. We will never classify A-8, that's a peat or organic soil. They will never ask you, okay? There are other methods to classify that soil. So for this soil sample C, without doubts, it is A-7. Now, you know The PI of this soil is 31. Okay, and this PI value has to be tested or checked against the liquid limit minus 30. When you do liquid limit minus 30 for soil sample C, what is the value? Can you give me that? It's 41, right? So the PI of the soil is 41. PI of the soil is 31 and the test value is 41. So PI of the soil is less than liquid limit minus 30. Is that correct? Because PI of the soil is 31 and liquid limit minus 30 is 41. Therefore, PI of soil sample C is less than the value given by liquid limit minus 30. Therefore, soil sample C should be A-7-5. Plasticity index of A-7-5 subgroup is equal to or less than liquid limit minus 30, and we just did that. 31 is less than 41, therefore your soil sample is A-7-5. Okay, so we'll pick up that one. Once you know this is A-7, you need to calculate the group index GI, and group index GI is given by this equation. Right, this alone is called partial group index, but this plus this will give you the group index itself. And put the percentage passing the number 200 sieve as given here, 87%. Liquid limit is 71. Percentage passing through number 200 sieves 87, and PI is 31. So if you run the calculations, you will get 33.58. You have to report it in the whole number. It's 0.58, so report it as a 34. Okay, 33.58, report it as a 34. So this soil sample C is A-7-5, in the parenthesis it's 34. So this is how you will classify the soil based upon the ASTO classification system. Time now is 8:13. You want to take a 5-minute break or continue? Okay, 5 minutes will keep us 8:17. Let's meet at 8:17, okay? Or 8:18, okay. Correct, hindrance, yes, so sorry to say that, I saw the notice. Yes, they have cancelled the exams on schedule on April. So the spring is gone, so the next exam would be in October. You have to wait for about 6 months now. I do not know that. It's up to the NCEES. It's up to them, right? So I wish they could take it. Because of the coronavirus epidemic, I think they cancels the exam. Okay. School of PE should be in contact with them, or so definitely all of you will have a notice or email from School of PE when they will schedule the exams. But so far I know is it has been cancelled, and the next exam is in October. So it means you have a lot of times to prepare for your exam. That will be very nice. If they have provided you the access till October, then you can go through, you can use it. Please make use of that. That will be very, very good. Alright, so it's good that School of PE has provided the access till October. That's good. Alright, let's give a cup of coffee, then we'll come back again, okay? Thank you. Alright, next, another soil classification system is based on Unified Soil Classification System, or USCS system. Okay. Christine, can you take a poll to check how many people are actually attending this class? There are 58 students in this class right now. Stephanie or Christine, right? Anyway, let's move on. Okay. Based upon USCS systems, the particle size definition is as given here. Gravel, anything as big as 3 inch and as small as 4.75 millimeters, or anything passing through 3 inch sieve and not passing through number 4 sieve. Sand, anything passing from number 4 sieve and not passing from number 200 sieve. Silt and clay grouped together, and anything passing through number 200 sieve is grouped together as a silt and clay. Okay, so if you compare with the ASTO systems, the particle definitions for gravel based upon USCS system is anything from 3 inch to fractions not passing through number 4 sieve is defined as gravel, whereas in case of ASTO it is number 10. So it was number 4 in USCS system, number 10 in ASTO system. Sand, anything from number 4 to number 200 in ASTO, from number 10 to number 200. Okay, let me ask you one question. When I say number 4 and number 10, which sieve size will give you bigger particles? Which sieve size will indicates bigger particles? Number 4, right? As I told you, if the sieve number increases, particle size becomes smaller. So ASTO is confining to the smaller size compared to the USCS system. Okay, that's very good. For the fine grained soil, silt and clay, we perform outer limit test for the USCS system. We are as good as liquid limit, plastic limit, or PI is known, so we are good. In case of ASTO, we will still do the gradations, particle size distribution of gradations by performing hydrometer analysis. For the comparing point of view to the coarse grains and fine grains, we will keep 50% for the USCS systems. Anything passing through number 200 sieve is less than 50% is called coarse grain soil. Greater than or equal to 50% is called fine grain soil. Whereas for the ASTO, percentage passing through number 200 sieve, if it is less than or equal to 35, is defined as coarse grain soil. Whereas in case of fine, it should be greater than 35. So the comparing percentage is also different. So these are the things you have to keep in mind. Okay. So just know these are two different systems. In case of ASTO, we use the table. In case of USCS system, we will also use the table. But before that, we should know for the USCS system, your job is to find the first letters and second letter, just 2 letters. As long as you know you have the technique how to find the first letter and second letter, you are good to classify the soil based upon USCS system. Your first letters could be gravel, G for gravel, S for sand, M for silt, or C for clay. Organic will not do. And your second letter, if your first letter is gravel or sand, then the second letters could be either P, W, M, or C. P stands for poorly graded, W stands for well graded, M stands for silty, C stands for clay. Or if your first letter is either silt or clay, M or C, then second letter should be either L or H. So these are the technique, right? Sounds pretty straightforward. Let's see what happens. For a USCS system, again, the classification procedures you can follow here. You should know the percentage passing to number 4 sieve, because you have to know the fractions of gravel, fraction of the sand, because this will separate between the sand and gravel, and percentage passing to number 200 sieve, because this will give you the fractions of coarse fractions and the fine fractions. And if percentage passing to number 200 sieve is greater than 50%, then the soil is the fine grained soil. So your first letter should be either M or C, right? For the fine grained soil, the first letter should be either M or C, silt or clay. In that case, if more than 50% is passing or equal to or more than 50% passing, you can use Casagrande plasticity chart, which is figure 2.6, and based upon liquid limit and PI value, you will get both first letter and second letter. That is pretty good, right? If 50% or more is passing to number 200%, then you simply use the graph, Casagrande plasticity chart, then you can find first letter and second letter. But it may so happen your soil percentage passing to number 200 sieve is less than 50%, and even that there are three categories. If percentage passing to number 200 sieve is less than 50% and your fine percentage passing to number 200 sieve fines are less than 5%, then you should know coefficient of uniformity and coefficient of curvature of that soil. Then you have to use the figure, which is a flow chart given in 2.4. You have to follow that flow charts. We'll take an example. Okay, if percentage passing number 200 sieve is less than 50% and your fine or percentage passing number 200 sieve in that case is greater than 12%, then again liquid limit and PI value of the past soil will be known. Then you will use the Casagrande plasticity chart to define the soil. But in both cases, your first letter should be either S or G, gravel or sand. Okay, and if the fine is in between 5 and 12, again, so you have to use the Casagrande plasticity chart, and first of all you have to use the figure 2.4 and Casagrande plasticity chart. We'll take an example also. So these are your USCS coarse grain classification flow chart. When your gravel fraction is more than sand, you will come here and look at the percentage passing through number 200 sieves and follow this line. So we'll follow this. Your job is come here, find the group symbol here. Okay. Similarly, if your sand fraction is greater than your gravel fractions, your soil is coarse grain soil, you will come up to here to find this group symbol. Okay. Yeah, if you find your review notes blurry, I think go to the School of PE's exam review guides. You can copy from there. Okay. And in case of the fine grain soil, if percentage passing the number 200 sieve is greater than or equal to 50%, then your soil is the fine grain soil, and based upon the liquid limit less than 50, you will follow this on liquid limit, and you will also only classify the inorganic soil, you will not classify the organic soil. And if your liquid limit is greater than 50%, again you will only classify for the inorganic soil, and the organic soil you will not classify. In case of if percentage passing to number 200 sieve is greater than or equal to 50%, I will recommend you to use this chart rather than following that figure 2.5. Follow this chart, because liquid limit will be given, plasticity index will be given, and since more than 50% is passing through number 200 sieve, so first letter as well as second letters for the soils will be obtained from here. Okay. So let's do this example. Please read it first. So it says determine the USCS classification of soil sample A, soil sample B. Sieve sizes are given here and percentage passings are given here. And also given here is liquid limit, PI, not the plastic limit, but plasticity index itself is given PI, right? You don't have to calculate PI, PI is given. And coefficient of uniformity and coefficient of curvatures for soil sample A is not given, it is not needed, but for soil sample B, it is given. Okay, so let's classify the soil sample A. If you look at here, percentage passing through number 200 sieve is 87%. Is this a fine grained soil or coarse grained soil? Can you tell me? It is a fine grained soil, right? Because more than 50% is passing through number 200 sieve, therefore it is a fine grained soil. If it is a fine grained soil, your first letter should be either M or C. Is that correct? If your first letter is either M or C, your second letter should be either L or H. Correct? Okay. If you know this much, then let's go and see. This liquid limit is 75 given. PI is 20. And let's calculate the percentage of gravel and percentage of sand in this soil sample A. Although the major behavior of soil sample A is controlled by the fine grained soil, even then let's find the percentage of gravel and percentage of sand. Can you find the percentage of gravel here? Zero, right? Why is that? Anything not passing through number 4 is gravel, right? The percentage retained on number 4 sieve is gravel. But in this case, for soil sample A, 100% is passing through number 4 sieve, therefore gravel is 0. What is the percentage of sand here for soil sample A? Right? Because from number 4, 100% is passing. From number 200, 87% is passing. Therefore, gravel is 0, sand is 100 minus 87, 13%. And fine is 87. See? So this is more than 50%. So your soil is a fine grained soil. So your first letter and second letter should be M or C, L or H. So in order to know that, let's plot these values in figure 2.6, which is Casa Grande plasticity chart here. Okay. So when the percentage passing through number 200 sieve is greater than 50%, then use this plot to find the first letter and second letter. So let's look at here. Liquid limit is 75. So this is your liquid limit, LL. This is your 70, this is 80, right? So 75 should be in between here. And your PI is 20. This is your PI value, 20 is here. So if you plot, the point lies here. It means below this line and right of this line, there are either MH or OH. Our soil is inorganic soil, so we will not classify OH soil. We will classify only the inorganic soil. Therefore, the soil sample A is without doubt MH. So this is a highly plastic silt. M is silt, right? So this is how we use the classification of soil, by using the Casa Grande plasticity chart. If your sample has 50% passing through, more than 50% passing through number 200 sieve. Okay, any question? Because OH, why not considers? We are not classifying the organic soil here. We will only classify the inorganic soil. OH is your organic soil. Okay. Similarly here, OL is your organic soil. OL, OH, these are your organic soil. And one more thing I would like to tell. This is your A line, right? A line. Sometime when you plot your value, this value could be on the line. If it is on the line, classify the soils as a higher side. So in this case, if it lies here, I will classify the soil as clay, highly plastic clay, right? Sometimes your point could like value of liquid limit and PI could like in this hatch area, this trapezoid hatch area. In that case, that indicates your soil has dual nature, CLML. This is especially useful when you are classifying the granular soil. Okay. Gyro, they should tell you this organic soil. For your exam purpose, they will not give you organic soil. Organic soil has other way of classifying the soil. Rather than this, there is other way. So they will not ask you to classify the organic soil. Okay. Let's classify the soil sample B. Is this a coarse grain soil or fine grain soil? This is a coarse grain soil, right? From number 200, only 10% is passing. Therefore, this number 200 sieve is very, very important. Number 200 sieve is a identifying gate. Percentage passing through it is always very, very important. In this case, 10% is passing, 90% is not passing. It means the other way, it is telling 90% of soil sample B are coarse fraction. It could be sand, it could be gravel. So let's see what percentage is gravel, what percentage is sand. Can you give me percentage of gravel here for soil sample B? It's 23, right? 77% is passing through number 4 sieve. Therefore, 100 minus 77 is 23. That should be your gravel. What is the percentage of sand here? 67, right? 77 is passing through number 4. 10% is passing through number 2. Therefore, sand is 77 minus 10 is 67. Gravel is 23. Sand is 67. Obviously, your fine, which is clay and silt, is 10%. So this is obviously 90% is a coarse grain soil. Therefore, it's a coarse grain soil. There are two flow chart. One, the percentage of gravel is more than sand. The other one is percentage of sand greater than gravel. In our case, for soil sample B, percentage of sand is 67. Percentage of gravel is 23. Therefore, the percentage of sand is greater than gravel. So we have to pick up that flow chart, which states percentage of sand is greater than gravel. So this we pick up because of this value, right? Sand is 67%, gravel is 23%. So after this, once you pick up this correct flow chart, then whether to go here or here or here, how do you do that? That is depending upon the percentage passing through number 200 sieve. 10% is passing. So from here, you need to move because it says 5% to 12% fine. Fine means particle passing through number 200 sieve. Okay, so only 10% is passing, which lies between 5 and 10. So you'll move from here to here. Okay, agree? Once you move here, you could go there or you could go there. First, go at the top. The condition here is C sub U should be greater than 6 and C sub C should be less than, greater than 1 or equal to 1 and less than or equal to 3. Right? So what does it mean? So if you look at here, C sub U is 26%. So C sub U is greater than 6, right? Because 26 is greater than 6. That is correct. But C sub C is 0.2. So 0.2, C sub E is less than 1. Therefore, this condition is not correct. Agree? What is what these statements tell you? This tells you this is like a limit in your calculus. If you remember your calculus, let's say if there is a line here, you have got two values, right? This is your one, let's say one limit, and this is another limit. Say this is your number 1. Let's say this is your number 3. So this tells you the CC should be in between this, right? Greater than 1 or equal to 1 or less than 3 or equal to 3. Mathematicals, this thing. So this is defining this thing, but for soil sample B, your C sub U is 0.2, which is here, right? So this is not correct. So once this is not correct, you have to move down. If you come here, C sub U is should be less than 6, but C sub U is 26. This is not correct. But if you remember the mathematical logic, in this case, either this or this. In this case, this and this both has to be correct. But in this case, one of them should be correct. This is not correct. So let's look at here. It says CC 1 should be greater than CC. So our CC is 0.2, right? So 0.2 is greater than 1 because, less than 1. So 1 is greater than 0.2. Therefore, this condition is met. So it means your value lies here. Either here or here, one of them, right? Either it should be greater than 3 or less than 1. For the soil sample C, your CC is less than 1. Therefore, this is correct. So once that is correct, one of the logic is correct. In that case, your soil is this. So from here, if you look at here, you have a soil classified at ML, MS, CL, CL, or CL-MS. So this means you need to look at the Casagrande plasticity chart because you have got liquid limit and PI. So if you go to Casagrande plasticity chart and your liquid limit is 22, 20 is here, just on right of 22 is there, and your PI is 5, that is your 4, that is your 4, that is your 7, so 5 should be just above the 4. If you plot, your point lies in this hatch area. This hatch area has been designated as CL-ML. So this is the CL-ML, right? Therefore, from here you have to move here. So your soil is SP, SC. Gems, little confusing. What is the confusing here? It says less than 1 but greater than 1. This is what we have to understand. This is only one value, right? So one value, it could be either less than 1 or greater than 3. Our value is less than 1, so that is correct. You have to understand, this is not soil mechanics, this is mathematics. Okay? So 0.2 is less than 1, so that's why that is correct. Very good, very good. Good to refresh the mathematics too, right? Any other question? If you want to take a short snapshots, please take it. Might help you, right? The 2 says, and the second part says, yeah, this one, mathematically this and this requirement should be met. In this is either this, or both of them. Okay, very good. Now, another soil classification system, sometime they may ask, and this is usually useful for your landscaping area. USGS system is like for buildings, right? General purpose. But USDA, this is for your landscaping architects. They could use it because it's basically used for agriculture purpose. And again, it will define coarse fragments for anything greater than not passing through number 10 sig. SP-SC. SP-SC. Right? SP-SC. And sand is anything passing through number 10 sieve, not passing through 0.05 millimeters. Look at here. As the classification system changes, definition of the soil particle also changes. Okay? Silt is passing through 0.5 and not passing through 0.002 millimeter sieve. Clay, anything passing through 0.002 millimeter sieve is clay. Here we will calculate the percentage of sand, percentage of silt, percent of clay. We will not calculate percent of gravel. because in agriculture, gravel is not useful, right? So percentage of silt, percent of sand, percent of silt, and percent of clay, when you add them together, and if it is 100, then you can use this USDA soil classification chart, which is this. This is a triangle, right? Here, it is a percentage of sand. You have got 0% here, 100% here, 10, 20, 30, up to 100 here. On these sides, you have got clay percentage, or clay separate, running from 0% here to 100% here. And silt fraction is presented here, and 0% here, 10, 20, up to 100% here. When you draw, because there are different lines inside, right? When you draw the line, make the line from sand to clay, clay to silt, silt to sand. Move in a clockwise direction, right? Draw the line in a clockwise direction, following the clockwise direction. So, if that's the case, we will classify the soils wherever that point lies. There are different area, highlighted area on the area classifying the soil. So let's take an example. Soil sample A, percentage passing to number 10 sieve is 100, number 200 is 90, from sieve 0.5 millimeter sieve is 85%, from 0.002 millimeter sieve is 60%. Okay, so in that case, can you give me the percentage of sand here? What is the percentage of sand? Anybody? Indent says 15%. Gyro says 10%. Corner goes with 10%. Joshua 5%. Okay. Stephanie 15%. Okay, hindrance 15%. Confirm that. Stay with the 15%. Very good. Again, as per USDA, sand is defined as anything passing through number 10 sieve and not passing through 0.5 millimeter sieve. Okay, this is not USCS. USCS was number 200, right? And number 10 is referred to ASTO. Remember, number 4 was your USCS, number 10 was ASTO. For the ASTO, number 10 to 200. But in USDA, it's not number 200, it's 0.5 millimeter sieve. Therefore, the sand should be 100 minus 85. That's 15. If that is the sand, what is the definition of silt? Please look at your page and tell me what is the percentage of silt. It's 25, right? Because anything passing through 0.5 millimeter sieve and not passing through 0.002 millimeter sieve is silt. Therefore, your sand is 15%, silt is 25%, and your clay is 60%, right? So now, when you add 15 plus 25 plus 60, is that 100? Okay, if it is 100, then you can plot these fractions on that textural chart here. Your sand is 15%, this is your 0, this is 10, this is 20, 15 is in between 10 and 20, clockwise from here to the clay. And your clay is 60%, this is your 0, 10, 20, 30, 40, 50, 60, from clay to silt. And from the silt is 25%, this is your 0, 10, 20, 30, 25 is here. If you draw, all the three lines are concurrent or meet here. And this highlighted area is designated as clay in this textural chart, right? Therefore, your soil sample A is classified as clay. Any question? Very good, yeah. Now, let's say soil sample B. Can you give me percentage of sand here? What is the percentage of sand? 17. Okay. Very good. 32. All right. Percentage of silt? 47. Okay. And percentage of clay? No need to calculate. It's right there. 21, right? So, only 85% is passing the number 10 sieve. How many percent is not passing through 10 sieve? 15%, right? So that 15% is a coarse fraction. So the coarse fraction is 100 minus 85, that is 15%, which is here. Sand, you told me 17%. Silt, told me 47%. Clay, 28%. Perfectly fine. When you add 17 plus 47 plus 21, is that 100? So it is not 100, means we cannot plot these values. This means we need to normalize these values, alright? The normalizations will be performed. When you add them, all of them, it is 85. Therefore, to normalize the sand fraction, 17 divided by 85 multiplied by hundreds give you 20%. Similarly, to normalize the silt fraction, 47 divided by 85 multiplied by hundreds give you 55%. Similarly, clay, 21 divided by 85 multiplied by 100 give you 25%. Now, if you add 20 plus 55 plus 25, is that 100? Okay. Normalization part is when you add, first of all, add the fraction of sand, fraction of silt, and fraction of clay. When you add them together, if it is not 100%, then you cannot use this value. You cannot plot this value on that Traxler chart. So this indicates this value has to be normalized. And normalizing process is whatever aggregate value you get, 17, in this case 17 plus 47 plus 21, aggregate value is 85. So whatever you have got aggregate value here, the fractions divided by the aggregated value, 85 here in this case, 47 divided by 80, aggregate value 85, 21 divided by 85. Convert this into percentage, then you will get this fraction, and when you add them together, it's 100. Okay, now you can plot these values. So bring that table, bring that chart. Your sand is 20%. This is your 10, 20 sand. Your clay is 25%. This is your 20, this 10, 20, 30. So 25 is here. And your silt is 55. This is 10, 20, 30, 40, 50, 60. So in between is 55. So point lies here. So the highlighted area is silt loam. We'll call it silty loam. So soil sample B is classified as silty loam. Okay. This is how you'll use the process of classifying the soil based upon USDA. It seems like you can get the correct classification using only two. Yes, Timothy, but you have to use the third one also. Okay. Because two lines, the value of two lines will not give you 100%. If you add them together, it will not be 100. So the third line is your concurrent value. That will make sure it is 100%. Yes, draw the line from sand to clay. Sand to clay. And clay to silt, silt to sand. Clockwise direction. James. That will be also same thing. What he's saying is the other way around, right? Anti-clockwise. If that is good for you, follow the anti-clockwise. Any direction you want to do it, you will get the same answer. Yeah. Okay. All right. This brings the end of our chapter 1 and chapter 2. Time now is 8:55. Let's review the solution. We'll go work on the workshop problem chapter 1 and 2. We'll review the solution at take 5-minute break. Let's say 9:30. Okay, 9:30. Let me put that here. You are doing workshop problem. See it here.